Hello everyone and welcome to this lecture on analog integrated circuits. Today we're going to start module 2, device models and common source stages. So the outline for today's lecture will be, first we're going to study the transistor MOS large signal model, then we're going to study the MOS small signal models. We're going to talk about submicron effects in CMOS devices, and we're going to have an introduction on common source amplifiers. So first we have that MOS devices, as you have seen in previous courses. We have here our MOS device, so gate, source, and drain. The current in these devices can be modeled using the following equations. So if we plot the drain to source voltage and the drain current, we will see that for different VGS values we will have something like this, following voltages. Okay, and then in this region we will see that the following equation holds. So we have that the first equation that we call it in the linear region. It is the one that that models the current in the transistors, and then we call it the linear region because, as you see, it resembles the curve of a resistor. No? So the curve of a resistor looks like this, voltage and current. So we call it the linear region, and then we can actually calculate the resistance here. The resistance will be equal to the VDS divided by the current, and that current will be mu COX. Then we have VGS minus VTH VDS minus VDS square divided by 2, and then we have that this goes, and this resistance will be approximately COX, and then we have VGS minus VTH, and then term that depends on VDS also. Very often the VGS minus VTH it is very large. For instance, we are working in these curves, and VDS can be very small, so that will be the following region here, working in this region here. Then this term, it is very little and can be omitted. Okay, and then we have a equation that depends only on VGS and VTH. So this equation tells us that we can build a resistor that change in value. It is a variable resistor. So the transistor in this region behaves as a variable resistor, and we can change this slope. We can change this slope by changing the gate to source minus VTH voltage. So when we increase or decrease VGS, we can change the slope of this curve and then change the resistance. So this particular case, we have it in the linear region. The transistor behaves as a resistor. Above particular voltage, and in this particular case it is when VDS it is larger than or equal than VGS minus VTH, then we have that the current plans out. Okay, the current becomes saturated, and then it is pretty much constant. We call this region the saturation region, and then we can see that they are almost horizontal curves. In this region, the transistor works as a current source. Okay, it is not a perfect current source, it's not an ideal current source, it has some slope, and that is modeled by this. So we see that it is going, normally is going up a little bit, it has a positive slope. So this becomes interesting because we can change the value of this current source by changing the value of VGS minus VTH. So each value of VGS will produce a different amplitude in this current source. So we deal this as a variable current source. Okay, so this is interesting because then we can use this device for amplifying voltage to current. So it is transforming voltage to different current values, and yeah, this the region in which transistors work when we are building amplifiers, and in which we are going to be working most of the time when we are working in strong inversion. Now in weak inversion, we have that VGS, it is lower than VTH. Okay, so in the previous example in saturation, we have that VGS, it is larger than VTH. Sometimes we call it that the transistor it is on in this state, but actually VGS doesn't need to be higher than VTH for the transistor to conduct. So the transistor it is actually already conducting current under VTH. So there will be some current that it is flowing. It will be much smaller than the current that flows in strong inversion, but there will be already some current that it is flowing here, even though it is under the threshold. And then we call it the weak inversion, and the equations that govern this region are the following ones. So we have that the drain current in most transistor in weak inversion, okay, so we can call it EDS, is equal to IOS, and IOS depends on the mobility, depends on the oxide capacitance. Phi is a thermal voltage, that it is kT divided by Q, around 25-26 millivolts at room temperature. It depends on the dimensions of the transistor, and it depends also on other parameters like the inversion coefficients. So we plug in this equation here, and we are going to assume that it is dominated by this factor. We will assume for a second that this is plugged in here. Then we have that the following equation resembles very much equation that we have seen before in bipolar transistors. So we're going to delete this here. So we have an exponential curve. And we have an exponential dependence with the VGS, and this is multiplied by 1 minus A minus VDS divided by thermal voltage. Okay, so when we plot the curves, for this transistor, VDS, EDS, they will have similar curves as they have in the strong inversion. It will look like this. But we have this term here, that decreases for small values of VDS, So we have that if a VDS it is larger than around 4 thermal voltages, and that will be higher than 4 times around 25 millivolts, so around 100 millivolts. These terms can be omitted. Okay, that will be x raised to minus 4, and that is a small, very small value. Then under this condition, this term disappears, and then we have a much easier equation here, that it is just the first exponential, VGS divided by thermal voltage. So, and then it means that this is for sigma t around 100 millivolts. These lines becomes almost horizontal. Okay, there is going to be some still some dependence on some slope here. Okay, there is going to be some slope. These curves are going to be growing, but yeah, they will behave like a current source also. It is behaving also as a current source. So we will be working in this area when we are designing amplifiers in weak inversion, and of course we should avoid this one because here there is no amplification. Okay, how we characterize the transistors, and probably you have done that in previous courses. We need to do double sweeps, and you will be doing that as when you create your setups for the first lab. I have already done this one here. There is some videos that you will use during lab 1 in order to create your test setup. So we just put voltage sources, connect to the transistor, and then we will use ADXL to create the double sweeps. Now, for instance, I'm going to sweep VGS and gains VDS with steps of 50 millivolts. So I have created a test. Again, there is a tutorial for you to do this that is online that you are going to use. So I set up the DC sweep with 40 millivolts steps, and the external sweep will be VDS in steps of 50 millivolts. We run it very quickly. Okay, we are almost done. And then we can see the course of VGS, ADS versus VGS for different values of drain to source voltage. So the first one is 0 volts. So 0 volts, it means that this is in the linear region. Okay, VDS it is smaller than VGS divided the VGS minus VT. VT in this technology it is around 0.4 volts. Then when we start increasing VDS, yeah, we see that slowly the transistor entering saturation, and then we see that the slope plans out. Okay, it converges. So these are the curves for this transistor here. If we wanted to do the other sweep, then we can set this one to a particular voltage, for instance 1 volt, and then I'm going to change this. And add a specification from 2. We put linear, and you can play with these values. Let's start in 0. The step size, let's say 50 millis, up to 1.8 volts. Okay, so we have here, and we're going to run the VDS sweep. So in this one, what I am doing is I am sweeping VDS voltage in the internal sweep, and in the external I am sweeping VGS here. So we run the simulation. Okay, we're done. We plot it, and then we have the output characteristics. Okay, so it is drain to source voltage versus currents for different VGS voltages. Okay, now we can identify here the weak inversion. Weak inversion is when the VGS is under the threshold voltage. So threshold voltage for this technology is around 400 millivolts, 450. So we can see that these curves here are sub-threshold. Yeah. And then the transistor entering in strong inversion, and then we see these curves that then takes over the quadratic equation. We see the slope also here. Now, sometimes it's practical to use the logarithmic scale to see better the sub-threshold. So you can see here 100 of nanoamps, tens of nanoamps, and 2 microamps. So we have around microamps here, and then above we can see that it starts getting slower how it grows, and it is because we enter in the quadratic equation. So then it grows much more slower, the current, in comparison to the sub-threshold. So let's continue with our lecture here. So these are the curves of our transistor. At some point we will want to decide where our transistor should work, and then we will define the operating point for the transistor, and we will use these curves to exactly point out exactly where it will be. For instance, let's say that this is VGS of 1 volt, for instance, and I want it to work it in 0.9 volts. That will be here. That will be around 0.45, something like that, milliamps. So this point is going to be my Q point. This VDS is going to be my VDS Q. This is going to be my VGS Q, and this is going to be my EDQ. So we take these curves mainly to find how much margin I have before the transistor leaves the saturation region. Remember that this saturation region will do something like this. Okay, so I can only work in this area here, because when we are passing this area, then the slope goes very quick down, and then it means that the transistor stops working as a current source, as a controlled current source. So I can put the Q point in any of these points in this area, but I have to be careful because this is a resting point. This is a QSM point. When information signals start coming in, this is going to move. So I have to make sure that for all signal swings that I have around my transistor, all the points have to be inside the saturation region. Okay, so you're going to make these setups for characterization of the transistor as part of lab 1. I have IDS of VGS. I already showed you in Cadence. I did it in logarithmic here. and we can see that when we put logarithmic, this grows logarithmic scale. The current grows as a line. Not surprising because we have an exponential function there. And for higher values of BGS, these start changing the slope. So here it is around this point we start entering in the quadratic equation. So here it is we can see around 1 microamp or 2 microamp for this particular transistor. Okay, this area is the weak inversion, and we have something that we call moderate inversion also. Moderate inversion. And then we have strong inversion. Okay, the moderate inversion is the transition between the equations that we have, the exponential to the quadratic equation. Yeah, and we can use this setup to check. Okay, so we go forward. We have that we know that the transistor works as a controlled current source, and we can use it in order to amplify signals. For strong inversion, we can extract a small signal model for this control current source, and it will take the following parameters. And then we have two kinds of transistors. We have a NMOS transistor here, and then we have the PMOS transistor here. The model is valid for both transistors. So when we derivate the curves of IDS versus VGS, we can extract the component for the transconductance. Okay, and it takes this value when we derivate that equation in the saturation region, and this is also equal to IDS divided by VGS minus VTH. Okay, so sometimes we can use one or the other. It really doesn't matter, they are the same. The slope in the output characteristics when we plot IDS versus VDS creates a resistance, an output resistance that we can calculate as 1 over lambda IDS. And then we have also another transconductance that depends on the bulk to source voltage. And this transconductor is small, but it exists. However, for most of the things that we are going to do, we are going to disregard this one, and we are going to have the assumption that the bulk and source voltage is the same. So when it's the same, this is equal to 0. So we're going to make a small mistake, but at the end of the day, we will see that it really doesn't affect our design. So this is just a simplification. Then we have a bunch of capacitors here. We have extrinsic and intrinsic capacitor. Then intrinsic capacitor are the ones that depend on the voltages that we apply to the transistor. So we see that for a NMOS transistor, it will look something like this. The NMOS transistor. You see this is the P substrate, N region, and then we have that poly it is located like this, and there is an oxide here between the poly and the substrate, and then there are several capacitors that are formed here. When the transistor enters in saturation, it is when VGS, it is VGS minus VTH, it is let's see. VDS it is higher than VGS minus VTH, and VGS is higher than VTH, so the transistor is on, and then we are in the saturation region. There is a channel that it is formed here, so we call it this the source, this is the gate, this is the drain. There is a channel that is going to be formed here, and yeah, this channel looks like this, and that channel will allow charges to move between the source and the drain. And interesting for us right now is that there will be capacitance that are intrinsic to this channel. So there is a capacitance that it is formed between the gate and the source. So this capacitance here, it is formed here, and this capacitor takes this value, 2/3 of Cox and the dimensions of the transistor. When we draw the transistor, when we saw from the top view of the transistor, it will look like this. We have the length, we have the width, the transistor will be here. So basically it will be 2/3 of the whole area multiplied by the C oxide when it is in saturation and in strong inversion. So this is an intrinsic capacitance here, and then we have also extrinsic capacitances. As we see that the poly extends over the drain and the source, so there is going to be a capacitance CGD that it is caused because of this overlap. So this is an extrinsic capacitance, that it is an overlap capacitance multiplied by all the width. So we have this extrinsic capacitance here. We have for the gate to source exactly the same thing. We have also an overlap capacitance here. There is also this overlap capacitance that is formed. We have already talked about this. We talk about the output resistance, and then we have also that there is some capacitance that appears between the gate and the bulk. It is also dependent on the amount of inversion that it is in the channel. So it's because this channel that is formed is the one that basically connects the gate to the bulk. So it depends on that. So we have some bulk to source capacitance. Sorry, it is from the source to the bulk. We have some capacitance here. That is this capacitance here. That is the one that it is an intrinsic capacitance. We have capacitance that depend also on the junctions. This is a diode here, there is a diode here. These diodes are reverse biased during normal operation, but they introduce also some capacitance here. So this actually this intrinsic capacitance CBS, it is caused by this reverse bias diode. And yeah, we have extrinsic capacitance also that we have to take in consideration. Okay, so basically this capacitance will change our model. If we add our capacitance on our circuit, we will see that there will be capacitance from gate to the bulk, gate to the source, gate to the drain, drain to the bulk, and actually there will be another drain to the source. And yeah, as a first approximation, we will assume that the bulk is going to be Vs, and then this capacitance will disappear, and CGB will appear in parallel to CGS. Now that will simplify a little bit our model for whenever we do circuit design without introducing a huge error. in weak inversion, the model is similar, but the values of the parameters are different. We have that the transconductance, so when we have the drain current is equal to, it will be VGS divided by phi10. We derivate this one, the VGS, that will be equal to, so we have this coefficient T I0 Ks VGS sigma T, and then this is equal to IT. So this is the transconductance. So at the end of the day, we will have that the transconductance will be equal to ID multiplied by Ks divided by the thermal voltage. Okay, so this is what we have here. And now think for a second. In the previous case, we have let's put it very quickly here. The transconductance grows with the square root of IDS, but in weak inversion it grows with linearly with IDS. So the first conclusion that we have here is that in weak inversion we get much more transconductance for the amount of current that we put in the transistor. Yeah, something that we already saw in the curves, that it grows linearly and then the slope starts to go down when we plot IDS versus VGS. RDS, yeah, we have the output resistance as we discussed before. VDS has to be larger than around 4 thermal voltages, around 100 millivolts, and then we have a high resistance at the output. So this will be a requirement when we are working at weak inversion. And then in weak inversion, we don't have the capacitance, the intrinsic capacitance that we have in strong inversion, because that channel it is not really formed, or that it is not so formed so strongly. So what we have, it is mainly the extrinsic capacitances. So both CGS and CGD, we draw the transistor very quickly again. So we have here N region, that will be source, gate, and drain, and actually there will be some overlap here, overlap on the regions. So what we will actually have, it is only this overlap capacitance here, and some capacitance to the bulk. Okay. So we will have the overlap capacitance that are still there, and some capacitance that is proportional to the area of the transistor. That depends pretty much on the inversion coefficient. The intrinsic capacitance are very small, so we can at some point disregard these ones. Now, when we are working with the modern transistors, we have that these equations that we have studied can differ a lot, and one of the problems that we have, it is that in short channel devices that are biased at pretty much higher voltages, we have that the drift velocity saturates. Okay, so we have our transistor here. We have oxide. We have the poly, and region. So in modern transistor, this distance, the length of the transistor is very small. The length of the transistor is very small, so we can draw the transistor like this in 3D. So this length it is very small, and then there are very strong electrical fields between the drain and the source. Okay, so we might think that we have very strong electrical fields. We can send very charges can move extremely quick, but it is true only up to some time. The saturation velocity in silicon, it is around 10 raised to the 5 meters per second, and above that the charges cannot move faster than that. So what it means for us is that the quadratic equation doesn't hold anymore, because then we have to take into consideration that electrical field, the saturation of that electrical field, that depends on the length of the transistor. So what we see is that when we apply a large gate to source voltage, and then the overdrive voltage that we call VGS minus VTH, it is much larger than the saturation electrical field times the length of the transistor. Then what we have is that this disappears. This is simplified. This simplifies with this, and then we have the current depends linearly on VGS minus VTH. It doesn't depend quadratically. And then when we derivate this equation, we have that the transconductance becomes constant. So it doesn't grow anymore with VGS VT, meaning that it doesn't work very well as an amplifier anymore. It doesn't amplify more. So we can increase VGS or VTH, but it will not improve the amplification. So it doesn't work. We cannot just apply the trick that we continue changing VGS and change the curve. So it will just saturate at this value. Then we have other kind of issues like drain-induced barrier lowering, as DBL. What we have is that when the length of the transistors get scaled down, the threshold voltage also goes down. The threshold voltage goes down, so we see that the following problem. So we have the transistor here, the poly, we have source, gate, drain, and regions. Okay, so when the length of the transistor start becoming very small, there is threshold reduction. Okay, so for very small threshold it will start conducting, and then we have the problem that there are going to be charges that jump from the drain to source to drain. So there will be a subthreshold conduction or leakage currents also that will appear. Okay, so normally they are very small, but the problem is when we have many of these transistors, the leakage current can really be very problematic.